Welcome to this video on hypothesis testing for two means when we have dependent samples. We'll start by defining independent and dependent samples. Independent samples are samples selected from two or more populations in such a way that the two samples have no influence on the probabilities of the other samples. Dependent samples, however, are selected in such a way that the values from the one sample are matched with the values from a second sample for the purpose of controlling for factors that are not important to our study. So we're going to run through an example here. We have a treadmill manufacturer that has developed a new machine with softer tread and better fans. This is better than its current model. The manufacturer believes that these new features will enable runners to run for longer times than they could on its current machine. To determine whether the desired result is achieved, the manufacturer randomly selected a sample of 35 runners. Each runner was measured for 1 week on the current machine and for 1 week on the new machine. The weekly total number of minutes for each runner on the two types of machines was collected. The question is, can the treadmill manufacturer conclude that the new machine has the desired result, that runners can run for a longer period of time on the new machine? We're going to conduct a hypothesis test to test this. So test at the 2% level of significance the claim that the new treadmill allows runners to run longer than the old treadmill. Now this is dependent data because we use the same runner to test the first machine and then the second machine. We want to be able to eliminate the extraneous factor of the runner. Our alternative hypothesis is that the average for new minus old should be positive. In other words, when we take the number of minutes that the person can run on the new machine and subtract out that for the old machine, we can see the gain in minutes that the runner had on the machine, assuming that it's positive. We want to prove that that number is positive. That's our goal. So we're going to assume initially that the new machine is no better than the old machine. In other words, the new machine doesn't add any minutes to what the runner is capable of doing. As always, we're going to put this on our graph. This is an upper tail test. We start by assuming there's no difference between the two machines, and then we attempt to prove that the difference between the new and old machines is something statistically higher than 0. Something up in the upper tail. We can test this in Minitab using a function called paired t. So we'll go to Stat, Basic Statistics, Paired t. Paired t will allow us to subtract out that human effect of the treadmill and just get the difference between the two treadmills. We may also use this if we're attempting to test humidity in the fields. We may test 6 patches in the field for humidity at one time period, and then a month later test those same 6 patches. We want to subtract out the effect of the patch and just see, are the crops drying out? So pick paired t. For our example, we have the treadmills in 2 separate columns. So we have each sample is in a column. We're going to put the new treadmill in first and the old treadmill in second. We want to be able to do new minus old. In options, we want to make sure that we have the right confidence level. The hypothesized difference, again, will almost always be 0. And then we want to make sure that we have the right sign in our alternative hypothesis. We're attempting to prove an upper tail test, so we want to make sure we have difference is greater than the hypothesized difference. We're trying to prove that the new is statistically higher than the old. So hit OK again, and we get our output. For those of you that like the t-value compared to the t-critical, you have your t-value here. I'm going to use the p-value approach. So we're trying to prove that the new treadmill will allow you to run statistically longer than the old treadmill. So the gain in minutes should be something greater than 0. Our difference then should be something in this upper tail. Our average difference for this sample was 22.33 minutes. That happens to have a p-value of 14.7%. Since the p-value is greater than alpha, we cannot reject the null. We do not have sufficient evidence to say the new treadmill outperforms the previous treadmill. So if these manufacturers are attempting to sell this new treadmill, saying it allows runners to run for longer, they're not able to prove that statistically. Thanks for watching. I'll see you again soon.